How do we split time series into training and test sets? This is a fundamental concept you will need to learn if you want to evaluate forecasting models. In this tutorial, we'll learn how to perform basic train test splits and a slightly more advanced version of that where we split the time series into training, validation, and test splits. We'll apply these methods to evaluate some ARIMA models. And as a bonus, we'll learn about how we can also generate ARIMA prediction intervals. As always, the Python code I use in the video is available online in Github. I'll link to that in the description below. If you find any of the code useful in this video, then please smash that like button and subscribe to the channel. I first worked on forecasting 20 years ago. That was in a food manufacturing facility where the managers simply had a statistical model that was fitted to data and it was predicting ahead. Now, a key step in their forecasting process that they had missed was model evaluation. So that's where a train test split comes in. We break our time series into two chunks. One is the training data, where we fit our model, and then the other is the test data, sometimes referred to as a holdout sample, where we test our model. We look at the performance metrics such as the mean absolute error when we predict that data. And it gives us a way to discriminate between different models and select what might be called the optimal model for our forecasting problem. We'll apply our methods to emergency department attendances from a UK hospital in the year 2017. The number of attendances ranges between 150 and 293 patients a day. Our forecasting task will be to predict 28 days of this time series. In this figure, we have the training data illustrated in blue and the test data illustrated in black. A key difference from traditional machine learning is that our train test split needs to take time into account. So we're effectively holding out the end of the time series that we will use to test our model. And the training data is all of the data that runs up to that final 28 days. I've included some code to perform a basic train test split for you on time series data. The function is called tsTrainTestSplit. That's going to accept an array-like object which contains your time series data in order. If that were a pandas data frame, it would also have a date time index. And we're also going to have a parameter called training size. That's an integer value that tells tsTrainTestSplit how much of the data is kept for training. That's going to return two array-like objects, either two pandas data frames or two NumPy arrays, depending on the type that you've passed in for TS data. Performing a train test split in Python is simplicity itself. All we're going to do is slice our time series data structure that we've passed in. If that's an instance of a pandas data frame, we'll slice using the iloc accessor. So we're going to go from the start of the time series all the way to and excluding the training size. This will be our training data, and our test data starts from the end of the training period and runs all the way to the end of the time series. Alternatively, if you've passed in a NumPy array or a Python list, we'll do the same thing, but we can use list and NumPy array slicing to return the same value. Let's have a go at performing a basic train test split and evaluating two ARIMA models on our test data. So we've got some standard inputs into our Jupyter notebook, pandas and NumPy. I'm also going to use the PMD ARIMA package because that provides us some ARIMA functionality, including an auto ARIMA function. I'm going to use some of my own software here, Forecast Tools, and that allows us to load the emergency department data, and we have a convenient mean absolute error function which we'll use to evaluate our forecasting models. There's a local Python module in the GitHub repo called tsplotting. That's just got some convenience function in it. Plot the time series in Plotly, and we've got some functionality for generating multiple ARIMA prediction intervals in one go. So to load our data, we call the load emergency department function, store that in the ED variable. We'll take a quick look at the head of that. So it's super simple data. We have a column of arrivals, which are integer values. These represent people arriving at an emergency department. And we have a date time index starting from the 22nd of January 2017. So to perform a train test split, we simply need to call the TS train test split function we defined. We pass in our time series, which is held within our TSED pandas data frame, and we pass in a training size, which is simply the length of the time series minus 28 days. So we can see that's give us 316 days of training data and 28 days of test data as we expected. Now, whenever I perform a train test split, my top tip is to just make sure that your code has worked as expected. So what I'm going to do is have a look at the final entry in my training data and the first entry in my test data. Those should be only 1 day apart. We can see that's worked correctly. So the time series training data ends on the 3rd of December and the test data starts on the 4th of December. So if you'd like to plot the training and test data, you can again call the plot time series method. We just pass in the training data and the test data. In this case, we're going to show the test data as lines. You can also set this to markers, which we'll use later on. If we want to zoom in towards the end of the time series, we just have to click the magnifying glass here and click and drag the part of the time series we're interested in looking at. So now that we've got a valid train test split, let's train some basic ARIMA models on the training data and try and predict that test set. Once we've done that, we'll compare the predictive performance of the ARIMA models using the mean absolute error. So we're focusing only on their point forecast here. The first model I'm going to create, I'm going to class as a benchmark for further ARIMA models. It's one of the most basic ARIMA models I can fit to the data. It's going to have a single autoregressive term and a single first difference. So we'll create the ARIMA object, store that within a variable called benchmark ARIMA. Then I'm going to call the fit predict method of that variable, pass in the training data as well as the number of periods I'd like to predict, and then assign the predictions, which will be a pandas series, into the benchmark ARIMA preds variable. We'll also take a quick look at the summary of the model fitted. So we can see, as expected, we've fit an ARIMA 110 to the model with no seasonal components. We have the intercept term and we have the lag1 AR variable. For our second model, I'm going to allow AutoARIMA to decide parameters. I'm going to set M to 7. So our seasonal period is 7 days. I'm going to pass in the training data and assign the return model to an object called ARIMA M1. Then I'll predict 28 days into the future, and we'll have a quick look at the summary of the model so we know what model has been fitted to the data. So AutoARIMA chose to take a first difference of the data and fit 2 moving average terms. There's been no seasonal differences taken of the data, but we have fitted 2 seasonal moving average terms. There's no intercept included in this model, but we can see we've got our 2 moving average terms, our non-seasonal components, and we have our seasonal moving average terms as well here. And because we set the seasonal period to 7, the first of those is 7 days in the past, and the second of those is 14 days in the past. Now, these statistics are about the training data. In old school forecasting language, we would describe these as in-sample statistics. But as a predictive modeler, what we're interested in is the performance of these models at predicting unseen data in the future, in our case 28 days. So let's firstly visualize the forecast performance against the training data. So here's our ARIMA benchmark performance. So the black dots in this chart are the test data. So we can see here, for example, on the 29th of December 27, the observed value, the ground truth, was 245 patient attendances at the emergency department. The point forecast of our benchmark ARIMA model, on the other hand, was around 219 patients. Here's the pattern of predictions we get when we apply our auto ARIMA derived parameters. So we can see that there is some seasonality included in the models initially, but that degrades to a straight line as we go further and further into the future. So on the face of it, the second model may be a better predictor, particularly of the earlier values in the time series test data. So what we really need to do is compare those two models quantitatively with the mean absolute error, the MAE, of the point forecasts. So what we can do is pass both of those to a function I've included here called create MAE data frames. That's just going to provide a nice summary of the data. We're going to pass in a list containing the models and the test data. And here's our results. So actually the models are very, very similar in performance. They're within a single person of each other. So even though the more complicated ARIMA model looked like it might be better, on average, over a 28-day period, there's very little difference between the two of them. A more complex strategy we can apply is a train, validation, test split. As the name implies, we're going to break our time series into 3 segments. We're going to have a slightly shorter training set, and that's going to allow us to predict a validation set of length 28. We're going to use the train and validation set for model selection. It's going to allow us to iterate multiple times through different models and allow us to pick which we think is the best forecaster amongst them. The test set is something we're going to put into a safe place. We're not going to think about the test set, and we're most definitely not going to look at the test set until we have picked what we think is the best forecasting model. The reason for that is we really want to use that test set as a simulated forecasting setting for our final model. We're going to train our final model on all of the data up to the end of the validation set and then predict test to get our final estimate of what we think model performance will look like. So I've created a second function for you called tsTrainValTestSplit. That's going to accept 3 parameters: our original ED time series, the training set size, and the validation set size. So we're going to have a validation size of 28. That needs to be equal in length to our final test period. And of course, then our training size is simply 2 times 28 subtracted from the total length of the time series. That function is going to return 3 pandas data frames to us: the training set, the validation set, and the test set. So taking a closer look at our train validation test split function. So it's only a minor modification of our original train test split. So effectively, we're going to create 3 array-like structures here. So again, we use array slicing. So the training data is sliced up to and excluding the training size. The validation data is sliced including the training size all the way up to the training size plus the validation set size. And the test data is simply from the training size and the validation size, i.e. from the end of the validation set all the way up to the end of the time series. And we return that to the user as a tuple. So while we're not going to look at the test set, I again recommend just checking that the end of and start of each of these sets line up as we would expect. So we can see that the end of the training data is the 5th of November and the start of the validation data is the 6th of November. So that's all fine. And then we can just check that the 3rd of December, yes, that lines up with the 4th of December in our test set. So with a train validation test split, our first job is to use the train and validation sets to select an optimal model. So the first thing I'm going to do is again set up a benchmark ARIMA model. That's going to be an autoregressive model with one first difference. We'll fit and predict the training data for 28 days. That's equal to the length of the validation set. Our second model will again be generated by AutoArima. AutoArima has selected the same model again from our shorter time series. So if we plot our AutoArima model, we can see that the forecast, the point forecast, follows the same pattern that we saw before, where we initially have some oscillations and then that gradually converges to this straight line. Taking a look at the performance of these models, we can see that our AutoArima selected model indeed appears to be superior at point forecasts. Okay, but let's not give up with just those two models. I'm going to see if I can beat that AutoArima generated model. So I'm going to add in an additional autoregressive term to the non-seasonal component, retrain the model, again with no intercept, and see if that beats our benchmark ARIMA and our AutoArima generated model. So we can see here that it actually generates no difference between the two models. The mean absolute error is identical. So on balance, I would probably go for our AutoArima generated model, as that has less terms. It's a simpler model. And as always, we prefer simpler models if they have the same forecast accuracy. So with a train validation test split, there's always a risk that we've slightly overfitted to the validation data, particularly if we've looked at it visually and if we have run multiple forecasting models through the validation data and adapted our models to see if we can improve our predictions. So the advantage of having this separate test set is we haven't looked at it and we haven't tested any models against it at all. So there is no chance of any leakage about information having fed into our forecasting process. So we can now retrain our ARIMA model with the same seasonal and non-seasonal components on the training plus validation data and predict our test set, then view the mean absolute error of that, and it will give us a simulated forecasting setting. It's our best estimate of what performance would look like in the real world. So we can see here that we've got a mean absolute error of 23.73. So that's on par with what we saw in our validation data. So we can be confident, or reasonably confident, that that's a good estimate of our forecast error, at least over 28 days in general. So we've used our train test split strategies, but all we've focused on is point forecast accuracy. Any good forecasting project should also at least take a look at the prediction intervals generated by forecasting models. So we trained our ARIMA model and called that final model. I'm going to call the predict method of the ARIMA model again, pass in the number of periods I would like to predict, but I'm also going to return a confidence interval. It's actually the prediction interval of the ARIMA model, and we're going to return a 95% prediction interval. I'm very quickly going to cast that to a pandas data frame and add in the date time index that matches the test data, so we can plot that. So what we end up with is a pandas data frame with lower and upper intervals by date. That allows us to easily plot that using the plot time series method, where we can pass in prediction intervals within a dictionary. We can actually pass in multiple prediction intervals if we need to. So here's our forecast, our point forecast, accompanied with our 95% prediction interval. It actually looks a reasonable prediction interval in this case for 95%. So most of the data is covered by the prediction interval, but at least one data point falls out of that on the 27th of December. You now understand that a basic train test split is the most fundamental concept to evaluate your forecasts. You should also be able to see that it's just a single piece of information. And basic statistical reasoning should tell us that if we can generate more than one data point, we have better information. To some extent, a train, validation, and test split helps us with that, as we at least have 2 data points we can work with for an individual model. However, there may still be a risk that we've been overfitting to our validation data, and so they might be quite different values we obtain in the validation set and the test set. So to go a bit further than what we've done, we'd need to think about a cross-validation approach. But that's a topic for another video. See you next time.